This is a very general title when I sent my abstract. Of course, it was very convenient because then I could, in the meantime, decide precisely what I would like to talk about. Of course, now I am obliged to say a few words about topological methods in discrete geometry, new developments, of course, from the point of view of our Belgrade school. So let's see. So I know that you have to press other or. Or it's the other way.
Opposite.
Okay.
Opposite.
That's very good. So I just want to, since this is not going to be a standard survey talk, but I will, because I would like to offer some details about some particular things, but still I will quickly pass by some topics. So I will show some slides with keywords and phrases and maybe titles. So please don't be offended if I'm very quick at some slides and then slow down somewhere else. But on this particular one, I want to point out that the third edition of this CRC edition of Handbook of Discrete and Computational Geometry should come out soon. Maybe it's already being printed. So chapter 21 is Topological methods in discrete geometry, and it is, in a sense, a survey of applications from the point of view of equivariant topology and the application of this configuration space test net scheme. These two papers that follow are more recent development, and actually the second one is included in this survey, but the others are not. And these are also some more recent papers. This is just a reminder. This will be the topic of the Thursday talk of Siniša Vrečica. I just remind you and myself about one of the fundamental problems where Weber theorem and Van Kampen-Flores theorem belong. It is the question of this general form. If you have a map from a simplicial complex, you ask whether you can find, for a given R, vertex describing faces so that they always overlap in the image. Now, there has been a lot of interesting developments in several past years, but the general problem is to characterize the simplicial complexes which are almost are non-embeddable. So almost are non-embeddable means precisely this. And, well, at least find interesting examples. And we are very far, I think, from solving this problem. It is the counterpart of the Kuratowski graph problem. We know exactly what are the obstacles for embedding a graph into the plane. There are two critical obstacles, these two Kuratowski graphs. There are similar results, but in general, we are still far away. However, the latest developments made it more, in a sense, we have more hopes that we can approach this problem more efficiently. Here, this is, of course, a familiar picture with Radon's theorem, but here I want to point out that not all Radon partitions are equal. Some of them are persistent. For example, in this convex position of points, you will always find this configuration, but this configuration is absent. So we will say that 2 points and 2 points partition is persistent, while this one is not. And here, it is really important that the difference between these two numbers is greater than 1. It is 3 minus 2. And this is maybe a glimpse of, this is classical, this is a glimpse of this latest result, the most general known, at least to us, Van Kampen-Flores type theorem which includes all known results of one Cantor Florence type, where you observe these conditions, difference by one is preserved. It is so-called balance case. But Sinisha, I believe, will talk more about that, and this is just a passing remark. Of course, this is related to some earlier work. This is some conditions, but now this is some consequences of that result, and now I'm really starting my lecture. Well, I like this statement. Allegedly, it was from a letter of Christian Huygens, of Leibniz to Christian Huygens in this year, and of course, many of you have seen this in the book of Glenn Braden, Topology and Geometry. We would like to believe that Leibniz in this statement somehow foreseeing homology theory, homotope theory, and possibly something new that hasn't come out yet. So homology theory is just linear algebra, but sophisticated linear algebra with spaces. And linear algebra is linear equations. And if you allow inequalities, it becomes also very interesting. And convex polytopes come into the picture, and of course linear programming. And then, what is the place of linear programming in the existing theory? And of course, for example, Robert Grice and his collaborators, there is this generalization of Max-Flow-Min-Cut theorem involving homological algebra. So there are developments in this direction, but here I just put linear programming as a key phrase, as a guiding key phrase for the rest of my talk. And I base my talk on two preprints, combinatorics of unavoidable complexes. There are, well, lots of us here, and many graduate students, of course. And the other one, Cyclohedron and Kantorovich-Rubinstein polytopes, also two graduate students, Filip Jeftic and Maria Jelic, and myself. And here is the beginning of my talk, and I slow down. I slow down a bit. Okay. Kantorovich is, of course, as we know, he's one of the founders, or the founder, of linear programming, or linear programming duality. And there is this famous Kantorovich result, and also Kantorovich-Rubinstein theorem. And this is well, not really a reminder about the Kantorovich-Rubinstein theorem, but a context where is the problem I wanted to study. And by the way, since finite metric spaces are very important for this meeting, of course, for persistent homology, the input is very often finite metric space. You construct, for example, Vietoris-Rips complex for a given metric space and a given threshold. But here we will see another construction and appearance of so-called Kantorovich-Rubinstein norm associated to a finite metric space. So just a few definitions. Once you have a finite metric space X with distance function R, then look at the vector space of all real valued functions, which can be also interpreted as weight distributions, which means sign measures. We allow negative measure to exist. And now sign measures with total mass 0. It is a vector subspace of the original space, so we denote it by V sub 0. And also we have the simplex of probability measures, so they all live in this vector space here. And here comes Kantorovich-Rubinstein. Let's denote by, so for given two measures, let's say positive measures, mu and nu, and let's assume that they have the same total mass. For example, they are both probability measures. Then there is a number, tau rho, of these two measures, which is the cost of the optimal transportation of measure mu to measure nu, where the cost of transporting the unit mass from x to y is precisely the distance, as you would expect. And here comes the key definition. This is a norm in this space, and we call it Kantorovich-Rubinstein norm. Now I will rephrase this somehow and offer maybe a simpler definition, although this one was very somehow theoretically explained what is going on. But here comes another definition, easier. Actually, now I will introduce Kantorovich-Rubinstein polytopes. So we have this vector space, and we have the norm, Kantorovich-Rubinstein norm. And of course, in a finite Banach or norm space, we have a unit ball, which is a centrally symmetric convex set. And this is a polytope in this case, and we call it Kantorovich-Rubinstein polytope associated to this metric row or metric space row. Explicit definition is the following. It follows precisely from the classical Kantorovich-Rubinstein theorem. Kantorovich-Rubinstein theorem says that it is one of the first duality type statements. It says that minimum value of some function is equal to the dual maximum value of some other. And in this case, maximum it is taken over some scalar product of all Lipschitz 1 functions over this metric space with the difference of these two measures. But we ignore this for now. We ignore it and just focus on the definition. So the definition says the following. Take the unit simplex. Well, in this language I can say unit sequence of Dirac measures, but that's too fancy way of the usual regular simplex spanned by vectors corresponding to the orthonormal basis. And then the distance between x and y is supposed to be equal to rho of xy, so I divide by this, in some sense making this a unit vector. So I turn this into a unit vector in some sense, and taking the convex half of these unit vectors, I obtain the unit ball, and I call this Kantorovich-Rubinstein polytope. By the way, this is just for the record. Kantorovich-Rubinstein polytope, as well as the associated this Banach space, with Kantorovich-Rubinstein norm, is complete invariant of the metric space. It completely describes the metric space. So this polytope has all the information about the metric, but as usual, when we look at the polytopes, classify them by affine isomorphism or even combinatorial isomorphism, which is a description of the posets, is not easy. What we find more reasonable as the first step is calculating f vectors and other invariants of polytopes. Whoops. Right. This is just an example. So this is if you take a metric where all points are equidistant, then the Kantorovich-Rubinstein polytope is a classical object. It is the convex hull of all the roots in the type A root system, and it's not difficult, well, to draw a picture in this one-dimensional case. And now here's the general problem posted by Anatoly Yershik. Study and classify metric spaces according to combinatorial properties of their Kantorovich-Rubinstein polytopes. And he discussed this before probably, but it was explicitly stated in this paper, Arnold Journal of Mathematics. And here is the result, which I will talk about a little. It says that that surprisingly enough, Cyclohedron, or the Barth-Taubes polytope, one of the famous polytopes, appears as the Kantorovich-Rubinstein polytope associated not to a metric. It's not possible because Kantorovich-Rubinstein polytope associated to a metric is centrally symmetric. Cyclohedron is not centrally symmetric. But it is, if we extend the construction to quasi-metric, so asymmetric distance function, so there is no symmetry in the definition, but it is a legitimate distance function, then it arises this way. And why this potentially interesting? Of course, there are some immediate consequences. I will just briefly mention some of them. This implies that the boundary, we know, I will speak more about it later, we know that the cyclohedron is one of the graph associahedron. So the first one is probably Stashev polytope or associahedron. Others are permutahedron, so cyclohedron, stellahedron, many other examples. So a corollary is that, well, this is a simplicial polytope being the dual, the polar of the cyclohedron, which is a simple polytope. The boundary is a simplicial complex, and it triangulates the boundary of the root polytope. So we have seen this picture. You can, well, maybe you can see that some of the faces are not simplicial, and it is always a corollary. We have a triangulation of this type. Now, I'll explain why later. This way we obtain as a corollary a result of Gordon and Petrov recent result, which we obtain independently but differently. And also we obtain as a corollary a result of Gelfand-Graev and Postnikov. They wanted to triangulate not the complete root polytope, but only the polytope generated by positive roots. Why? And for the reason they did that, it was in the study of generalized hypergeometric functions. You remember this famous book, Gelfand-Kapranov-Zelevinsky, was also written partly because they wanted to study, Gelfand wanted to study this problem. And this is about the same time. Now, maybe the main observation I want to make here, maybe our main observation here is that there is an interesting transparent connection between Kantorovich-Rubinstein polytopes defined in terms of metrics and nestohedra, so or graph associahedra. So these are two galaxies. Graph associahedra and nestohedra has been a subject in convex polytopes that has been studied a lot, and now it is in a very popular and interesting area. Now I'm just giving some images how, so this is a 5-dimensional cyclohedron, and we use images like this to record faces. In this case, the number of arcs corresponds to, it should be 1, 2, 3, 4, 5, so it's 4-dimensional, I guess. So it's 4-dimensional cyclohedron, and there are six vertices. This is, well, but this is a mistake. It should be W4 here. And this is just an indication what is going on. One should be able to see in this picture, these are two triangles. Each arc is a vertex. 3 arcs are 3 vertices spanning the triangle. These are simplices in the cyclohedron, and they appear hidden in the triangulation of the root polytope. Let's follow this story and see what's going on and why is this interesting. So as I said, I want to establish a connection with another world, another area in convex polytope theory. So if you have a subset of n, of this set of n elements, then the usual notation, there is a simplex spanned by f, which is just the convex hull of all basic vectors corresponding to F. It is, of course, a subset of the whole simplex. And if you have a collection of subsets, then you can take a Minkowski sum of these simplices. So taking Minkowski sum is, of course, an interesting operation, and the object we obtain is, for example, if you take Newton polytope of a polynomial, then it is then the Newton polytope of the product of polynomial is of course Minkowski sum of the Newton polytopes. So this construction appears in many situations. One of the central reasons this is studied in this theory of graph isohedra or nestohedra is this is how you generate simple polytopes. So, of course, in that case, H, this family, is not arbitrary. It is the so-called building set. So I'll just mention in passing what is a building set. If you know the definition, of course, it's simple. If you haven't seen it before, then it's probably more interesting to mention why people study building sets. Actually, this all started probably with the patent paper of William Fulton and Frederick McPherson, where they studied compactification of configuration spaces, of classical configuration spaces of ordered points on complex manifolds. And then continued by De Concini, Corrado De Concini and Claudio Procesi, who studied wonderful models of subspace arrangements. So you compactify complements of subspace arrangements. You define interesting, important, combinatorially rich compactifications. Eva Feichner and Dmitry Kozlov noticed that codified the combinatorial structure at the root of this construction. They call it incident combinatorics of resolutions, and of course use the language of building sets and nested sets and so on. And then, of course, in convex polytope theory, there are several contributions: Feichner, Sturmfels, Alexander Postnikov, Karl Devados. But I would also like to mention two logicians from Belgrade, Doshen and Petric, who are actually specialists in category theory and developed parallel theory, which turned out to be equivalent. So this illustrates the importance of this area of building sets of nestohedra, and our result really says that there is a contact between Kantorovich-Rubinstein polytopes and this area. And I will really outline this connection, give you an idea, even if you haven't studied before or this type of convex polytopes, nestohedra and graph-associated hydra. I will essentially show you some important ideas and give you all necessary information. So, all objects studied are Minkowski sums of simplices, and all the simplices are faces of the simplex you start with, you prescribe in advance. So I already defined what this means. So this is the Minkowski sum of some collection of simplices, and this says that this is how you can obtain the cyclohedron. By the way, cyclohedron was one of the nestohedra is Stashev polytope, which appeared very early, and you are probably familiar with the history of Stashev polytope, the isohedra. It is interesting that the cyclohedron, and also called Taub's polytope, appeared in the context of knot invariance. They wanted to generate systematically Gauss-type formulas. Gauss had this formula for the linking number in terms of differential forms. They wanted to similar formulas for higher order linking invariants, and they needed combinatorics of the cyclohedron or the Taub's polytope, the same polytopes that polytope that appears here. As a nestohedron, Wn, the cyclohedron arises as the nestohedron associated to the following building set. So you remember, the input is this family of subsets of the building set, and in this set, in this case, it is the collection of all proper connected intervals in the cyclograph. And this is a bit of the theory, which tells us that we can handle this object very successfully using combinatorial tools. By the way, just to remark from the other side, I mentioned that the importance of building sets stems from the fact that they produce simple polytopes. Simple polytopes are input for quasi-toric manifolds with some additional information. So this is also a big area of topology with toric actions related to toric varieties and algebraic geometry and many other things. Studying quasi-toric manifolds over nestohedra is also an active field of study. And studying combinatorics of this is essentially the same as studying algebra of the cohomology ring of the quasi-toric manifold associated to the corresponding polytope. Here I just point out that there is a description. Well, if F is an arbitrary family, which is not necessarily a building set, then you can still define the Minkowski sum delta F, which is not necessarily a simple polytope. But then, in order to understand better this convex polytope, you take what is called the building closure of this family, and then this building closure is easy to handle, and then you can express, for example, this polytope not only as a Minkowski sum, but also in terms of inequalities and one equality. And this number 2, this is the phase corresponding to some linear function. So this is just saying that you can handle this without problems. By the way, I have 15 more minutes, or
yeah.
So I'll speed up a little. I'm just saying that this general theory, with introduction of the new concept, so-called tight hypergraphs, which I will not explain now, leads to the following observation. If you take, in the case of the cyclohedron, in which case the graph is a cycle, and the building set is the set of all intervals, but now take the set of all smallest intervals, just edges of the graph, their associated building closure is precisely the building set associated to the cyclohedron. In this case, you obtain this zonotope as the associated convex polytope, and which satisfies this tightness condition. And the general theory guarantees the following. This is really the reason why we applied this approach. This theory says that if you take the cyclohedron, it is a convex polytope. It has many faces like this. Now, if you push these faces inside, but keeping them as faces, then you can lose some edges. It may be no longer simple anymore. This theory guarantees that by applying in suitable way this procedure, you can obtain from this cyclohedron, you can obtain this smaller object, this associated zonotope. And in this case, we can identify this zonotope as the generalized rhombic dodecahedron. And the proof is, look at the picture. now I won't do that because the time is running quickly. So I'll just say that these are the main ideas in one of the proofs of our central result. Okay. This is my first story related to linear programming in geometric combinatorics. This is now second story, more intimately related to the subject of, I started with the subject of further Computational theorems and so on. And here I report about the research in these two papers. And I still have good 12 minutes, so I can slow down a little now. This is new beginning. But here, again, I will be parsimonious, or how to say. Here is a simplicial complex. We introduce two invariants, partition number and the threshold characteristic. If you are familiar with r-unavoidable objects, which were very important, introduced by Blagojevich, Frick, and Ziegler in this very important paper in Bulletin of London Mathematical Society, partition number is really directly related to this r-unavoidable. Essentially, we say that partition number is less or equal to r if and only if k is minimally r-unavoidable. So it should say k is minimally r-unavoidable. I mean, it is r-unavoidable and not r minus 1 unavoidable. Probably many of you have heard about threshold complexes. So, unlike Vietoris-Rips complex, where you have a threshold for the distance function, threshold complexes in this sense arise in the context of a measure on your finite set. So you have a measure, and which measures, let's say, weights, puts some weights or importance on elements. You have some threshold, and then you take any subset and add up all the weights of the elements. If it is below the threshold, then you add it to the simplicial complex. That's called threshold complex. A standard construction used very much. So, in a sense, this invariant measures how big is the largest threshold complex contained in K. We are usually interested in this approach in evaluated partition number, evaluated from above. And this is a fundamental inequality, which is really elementary, which is pigeonhole principle in disguise. But let me, computing the threshold invariant of a simplicial complex turns out to be a problem of linear programming. And we were able to compute, sometimes by computer, sometimes for big simplicial complexes, efficiently this threshold invariant, and at the same time this provided an upper bound for the partition number. A complex is called intrinsically linear if we have equality, and otherwise it is called intrinsically nonlinear. Now, one of the motivations for our work is the following. Blagojevich, Frick, and Ziegler really had 4 examples of r-unavoidable complexes, and all of them are intrinsically linear. And we wanted to understand whether one can construct intrinsically nonlinear r-unavoidable complexes. In other words, complexes that cannot be proved to be r-unavoidable by pigeonhole principle in some sense. And one of our main results is systematic procedures for constructing intrinsically nonlinear r-unavoidable simplicial complexes. Let me say a few words about what you see here. So this is a front face of an icosahedron. And of course, we identify antipodal points on the boundary. So this is really a triangulation of the real projective plane. This is well-known triangulations. It is called hemi-icosahedron. It has 6 triangles, 6 vertices, and this is the minimal triangulation of the real projective plane. Real projective plane is together with complex projective plane, with quaternionic projective plane, octonionic projective plane or planes, and 3-element set. These are classical manifolds which look like projective planes, studied for decades by many Niels Kuipers and many other people. There is a complete classification. So they are essentially manifolds with 3 critical points, which are exactly 3 critical points. So in this picture, it turns out that we can put in this picture, well, for some interesting reason, instead of the hemi-icosahedron, we can put minimal triangulations of these other manifolds that look like projective planes. For example, complex projective plane. And this is a little chart showing, so what we are after. We want to maximize this. If this is 0, epsilon invariant measures, if it is 0, it means that the complex is intrinsically linear. So we want this to be big. The price we pay is the number of vertices in the simplicial complex. The method we apply is we use these manifolds, minimal triangulations of manifolds that look like projective planes. We take join. We can actually combine them, but here this is just only take one type and take nth join. And then we compute. Partition invariant is the same. This is threshold characteristics. And then we see how big that is. I mean, it is certainly positive. They're all intrinsically non-linear. They're all minimally intrinsically non-linear. And now, compared to the price you pay, you see somehow that these 3 examples are somewhat better than the quaternionic projective plane. Okay, I will just, since I have a few more minutes, this is essentially what I wanted to tell you, but just to remind ourselves what we are after and why was this studied, why we study unavoidable complexes, and in particular intrinsically nonlinear unavoidable complexes. Just quickly, with your permission, let me see, page down. So this is a lot of material, I had no idea, I had no plan to. So this is just to remind me that threshold complexes appear in game theory and cooperative game theory, and some of the questions we ask are related to questions of this type. And this is an algorithm, how you produce, that was the first question I mentioned, how you produce, how you systematically generate higher Kuratowski simplicial complexes. In other words, simplicial complexes that are not, that cannot be, that satisfy our Van-Kampen-Flores type theorem. So this is some sort of algorithm which I expressed in game theoretic terms. You have some voting game, and you produce, that's how you produce a simplicial complex, and you obtain the corresponding result. And this is just a reminder one of our early results with Siniša Vrečica, that when r is equal to 3, that complete the two-dimensional complex obtained as a join of 5, 5, 5 does not admit an embedding in three-dimensional space without triple intersections, and this is obtained from this voting game with the corresponding choice of parameters. And well, just to tell me that maybe another important thing to mention, in the first part I mentioned that Kantorovich-Rubinstein and nestohedra are related. Here I say unavoidable complexes are related to complexes like simple games that appear in game theory, in the cooperative voting game theory, and the question we ask should be really tested also in the context of the question asked in game theory. Well, thank you for your attention.
Are there any questions? Thank you very much.
Thank you.